Welcome to The Explainer. Today, we're going to talk about something that's happening literally everywhere all the time: motion. But to really get it, to talk about it like a physicist, we need to be super precise. So let's dive in.
So, let's just start with a really basic question. How would you actually describe something moving from point A to point B? You know, like a car's journey, or maybe a ball flying through the air. What are the absolute essentials you'd need to describe that movement perfectly?
And, your first instinct is probably to use words like fast or slow, right? Or it went over there. And that's totally fine for everyday chat, but it just doesn't paint the whole picture. When it comes to physics, we need a vocabulary that's way more specific.
And the cool thing is, that whole vocabulary, it's really just built on 3 core tools. Just 3 building blocks that let us describe any journey you can imagine, from a tiny snail crawling on a leaf, all the way up to a rocket ship blasting off into space.
Okay, let's get into it. Our very first building block, figuring out where something is. And inside this block, we've got 2 key ideas that sound kind of similar, but are actually super different: position and displacement. So yeah, everything kicks off with position. This is basically an object's exact address in the universe at one specific moment. You can think of it like dropping a pin on a map or just reading out some GPS coordinates. It's a snapshot in time. You are right here.
But of course, things rarely just stay in one position, right? The second they move, we have to start talking about displacement. And this is a big one. It's not just about how far you traveled. No, it's the straight line path. We're talking both distance and direction from where you started to where you ended up.
Okay, here's the best way to think about it. Imagine you walk 5 miles all the way around a circular track, and you end up right back where you started. So what's the distance you traveled? 5 miles, obviously. But your displacement, it's 0. A big, fat 0. Why? Because your final position is the exact same as your starting position. Displacement, you see, it only cares about the shortcut.
Okay, so now we know where something is and how far it's moved from its starting point. So block 2 adds the next obvious question. How fast did it do that? And this is where we need to understand the huge difference between speed and velocity.
And this brings us to a word we use all the time: speed. I mean, it's the number you glance at on your car's speedometer, right? It just tells you how much ground you're covering over a certain amount of time. It's really just a measure of how fast.
But here's the thing. Speed is only half the story. To be really precise, we need velocity. I like to think of it as speed's smarter, more detailed cousin. It doesn't just tell you how fast you're moving, it tells you where you're going. It's basically speed with a built-in GPS.
Yeah, this chart lays it out perfectly. Speed is what a physicist would call a scalar quantity. It's just a number, just the magnitude. But velocity, that's a vector. It has both the magnitude and a direction. So saying a plane is going 500 miles per hour, that's its speed. Saying it's going 500 miles per hour due east, now that's its velocity. And believe me, that extra bit of info is absolutely crucial.
Okay, so let's recap. We figured out where we are and we know our velocity, how fast and in what direction we're headed. But motion is rarely that simple and constant. So what happens when it changes? Well, that brings us to our third and final building block. And that change has a name: acceleration. Now in physics, acceleration is super simple. It's any change in an object's velocity over time. And notice I said any change. It's not just about speeding up. So this is the really crucial point. Acceleration can be any of these 3 things. You press the gas pedal, yep, that's acceleration. You hit the brakes, that's also acceleration, just, negative acceleration. But here's the one that always gets people: simply turning a corner. Even if your speedometer doesn't budge, that is still acceleration. Why? Because your direction changed, which means your velocity had to change.
All right, let's make this super clear. Just picture a car sitting at a starting line. Okay, 1 second into the race, boom, it's already doing 20 miles per hour.
Another second ticks by. Now it's up to 40.
And by the time we hit the 3rd second, it's at 60. You see that pattern, right? Its velocity is climbing by a steady 20 miles per hour times every single second. That steady change, that is its acceleration.
Okay, let's take a step back and see how these 3 blocks snap together perfectly to tell the complete story of motion. It's really elegant how each idea just builds right on top of the last one. You start with a position. Then you measure the change in that position, and you get displacement. Then you figure out how quickly that displacement happened, and that's its velocity.
And finally, you track how the velocity itself is changing, and that is acceleration. See, it's a complete story from start to finish.
And this is exactly why it's so powerful. I mean, understanding position, velocity, and acceleration, this isn't just about passing a physics exam. It's literally like learning the grammar of the universe itself. It's the fundamental language of how everything moves and interacts.
And the thing is, you are using this language all the time, even if you don't realize it. Your phone's GPS, it's constantly calculating your velocity to figure out when you'll get there. Every time you throw a ball, its velocity changes because of the acceleration from gravity. This isn't some abstract theory, people. This is the code that's running the world all around you.
So, I'm going to leave you with a little brain teaser to see if this all clicked. Imagine you're in an elevator, and it's moving upwards at a perfectly constant speed, let's say 5 miles per hour. The needle isn't moving. So my question is it accelerating? Really think about the definition we just covered. The answer to that question tells you everything you need to know about the language of motion. Thanks for joining me.
So, what if I told you that with just a few keys, you could unlock the secrets of motion? I mean, what if you could actually predict the future of a moving object, as long as it follows one simple rule? Well, today, that's exactly what we're going to do. We are cracking the code. We're diving into the kinematic equations, the actual language that describes how pretty much everything in our universe moves. This is the big question, right? This is our mission. Think about a car speeding up on the highway, or a ball flying through the air, or even a satellite just silently doing its thing up in orbit. How do we know, like exactly know, where it's going to be and how fast it'll be going at any given second? I know it sounds like some kind of magic trick, but it's not. It's just pure physics. Okay, so the entire system we're about to build, every single equation we're about to figure out, it all hinges on one single really powerful assumption. You could call it the master key that unlocks everything else.
And that one simple rule, it's called constant acceleration. And really, it's as simple as it sounds. You know when you're getting on a highway, you press the gas and your speedometer just climbs steadily, maybe from 30 to 35 to 40 miles per hour each second that goes by. That steady, predictable change, that's our foundation. That's all we need.
All right, so how do we take this rule and turn it into a tool that can predict the future? Simple. We're going to draw a map. But, not a map of a place. This is a map of motion itself. We're going to use a basic velocity time graph to literally see and decode an object's entire journey.
So this map has a really clear goal. On one hand, we've got something we can always measure pretty easily, time. And on the other hand, we have the secrets we're trying to figure out, an object's velocity at any given moment and its displacement, which is really just a fancy way of saying how far it's moved from where it started.
And here is where things start to click. Because we made that one simple rule, constant acceleration. When we actually plot velocity versus time, we don't get some crazy, unpredictable curve. Nope, we get a perfect straight line. And that straight line, that's our first huge clue. It's the visual proof that an object's velocity is changing at a perfectly steady rate.
Now this line is holding on to two major secrets. And to find the first one, all we have to do is look at its most obvious feature, how steep it is. So let's go ahead and interrogate that slope. You see, that steepness isn't just some random property on a graph. It has a real physical meaning. If the line is super steep, it means the velocity is changing really fast. That's high acceleration. If the line is flatter, the velocity is changing more slowly. That's low acceleration. In fact, it's even simpler than that. The slope is the acceleration.
So how do we get that number? Well, it's just that rise over run thing you probably remember from math class. The rise is just how much the velocity changed. The run is how much time went by. So when you divide the change in velocity by the change in time, well, you've literally just calculated the definition of acceleration.
And boom, just by rearranging that simple rise over run idea, we get our first decoded message, our first kinematic equation. It tells us that the final velocity, v, is just a velocity that started with v0, plus the acceleration multiplied by time, at. This is our first real key to seeing the future.
Okay, but wait, the slope was only the first secret. Our motion map has another one, and it's been hiding in plain sight this whole time. This time, we're not looking at the line itself. We're going to look at the space underneath it.
This, right here, might be one of the absolute coolest ideas in all of physics. That shaded area on the graph, it's not just empty space. It literally represents the object's displacement, how far it actually traveled.
So the graph isn't just telling us how fast the object is going, it's also telling us how far it went. How cool is that?
And the best part is, we don't need any wild, complicated math to figure out this area. We can just break that weird shape into two things we totally know: a simple rectangle on the bottom and a triangle sitting on top. The rectangle's area, that's how far the object would have gone if it never sped up. And that triangle on top, that's the extra distance it covered because it was accelerating.
And check this out. When we translate that geometry into the language of physics, we get our second masterpiece. You see that V0t part? That's the rectangle, the distance it traveled just by coasting. And the half AT squared part? Yep, that's the triangle, the extra distance it got from speeding up. We just turned a simple picture into an incredibly powerful predictive tool.
So from just those two basic ideas, what the slope means and what the area means, we can actually build out an entire set of tools. This is it. This is the complete kinematic toolkit for anything moving with constant acceleration.
Okay, so now we have our toolkit. The trick is just knowing which tool to grab for the job. Honestly, just think of it like a puzzle. Each equation is specifically designed to work even if you're missing one piece of the puzzle. As you can see right here, if you don't know the displacement, you grab that first equation. If you don't really care about the final velocity, that second one is perfect for you. And if you forgot your stopwatch and time is the big unknown, that third equation is your secret weapon. It's all about picking the right key for the right lock.
And that right there is why this matters so much. I know we've been looking at lines and shapes on a graph, but what we've really been doing is uncovering the fundamental rules that govern motion everywhere. I mean, from the simplest falling apple to the most complicated rocket launch, these are the rules of the road.
So, there you have it. We've cracked the code for a world of steady, constant change. But that does leave us with one last really interesting question, doesn't it? What happens when acceleration isn't constant? What happens when that straight line on our graph starts to curve? Well, that, my friends, is where the next chapter of physics begins.
What if I told you that you could tell the entire story of a journey, I mean, from a dead stop to a full-on sprint, using nothing more than a single line? It sounds a little crazy, right? But today we're going to see exactly how a simple graph can become an amazing storyteller for motion.
So, that's our big question. How can one simple line do all of that heavy lifting? To figure it out, we're going to follow a runner named Alex. We're going to track Alex's every move and turn this journey into a visual story one step at a time. You know, every story needs a canvas to be told on. For us, that canvas is a position versus time graph. And don't worry, it's way simpler than it sounds. The vertical axis, that's the up and down, just tracks where Alex is. The horizontal axis, the side to side, tracks when. That's it, where and when. With just those two things, we can map out pretty much any journey you can think of. Okay, so let's start at the very beginning. It's the easiest part of any story. Alex is at the starting line, all warmed up, but is not moving. Not at all. We're talking zero motion, just waiting for that signal to go. So if we look at the data, this is what we'd see. At second 0, Alex is at the 10-meter mark. A second later, still at 10 meters. 2 seconds go by. 3 seconds, you see the pattern, right? Time keeps ticking forward, but Alex's position is not changing one single bit. So just take a second and picture it in your head. If you were to put these dots on our position time graph and connect them, what kind of shape would that line make? How do you actually draw the idea of standing still? Yep, you got it, a perfectly flat, horizontal line. And this right here is our first huge rule. On a position time graph, a flat line means you're not moving. Zero motion. The position isn't changing, so the velocity is 0. Simple as that. Okay, bang, the starting gun fires. Alex is off and running, but not sprinting, just easing into a nice, steady jog. And that word steady is the most important word here. It means Alex is covering the exact same amount of ground every single second. We call this constant velocity. So what happens to our line on the graph? Well, we know it's not going to be flat anymore because Alex's position is changing now. So how do we draw this new, steady kind of motion? Our flat line completely transforms. It now becomes a straight, upward-sloping line. So the flat line for standing still becomes this steady, angled line for moving at a constant speed. You can literally see that Alex's position is changing by the same amount for every tick of the clock. And this brings us to an absolutely crucial idea. That steepness of the line, it has a name. It's called the slope. And on a position time graph, the slope is the velocity. If the line is steeper, it means a higher velocity. Alex is running faster. If it's a gentler slope, it's a slower velocity.
The biggest takeaway here is super simple. Slope equals velocity.
All right, the race is almost over. Alex sees the finish line and decides it's time to kick it into high gear. No more steady jogging. Alex is now sprinting, getting faster and faster with every single second that goes by. This change in velocity has a name too. We call it acceleration.
Now, if we try to draw this on our same old position time graph, things get, well, they get a little messy. Because the velocity is constantly changing, the slope has to constantly change too. And a line with a changing slope isn't a straight line anymore. It's a curve. It works, sure, but it's not nearly as clean or easy to read at a glance.
But what if I told you there's a much, much more elegant way to see acceleration? A way to take that complicated curve and turn it back into a beautiful, simple, straight line.
Let's just switch our whole perspective. Instead of plotting Alex's position over time, what happens if we plot Alex's velocity over time? This new type of graph is going to give us a brand new superpower.
And boom, just like that, all that complexity just vanishes. On a velocity time graph, our sprinter's constant acceleration becomes a wonderfully simple, straight, sloped line. And why does that happen? Because the velocity is increasing by the same amount each second. It's the exact same logic we used before, we're just applying it to a different graph. So let's lock this in. Acceleration is just the rate of change of velocity. And on our new velocity time graph, the slope of the line is the acceleration. See the pattern? It just repeats. The story of motion is always in the slope. Okay, let's bring all this home. We've looked at 3 different kinds of motion and 2 different kinds of graphs. But the real secret, the key that unlocks this whole story, is just understanding what the slope of the line is trying to tell you. It really just boils down to this. When you're looking at a graph of position versus time, the slope tells you the velocity. But when you switch gears and look at velocity versus time, that same idea of a slope now tells you the acceleration. It's really just 2 simple rules that let you read the entire story of motion.
So here's the whole thing in a nutshell. You see a flat line on a position graph? That object is at rest. You see a straight, sloped line on a position graph? That's constant velocity. And a straight, sloped line on a velocity graph? You guessed it, that's constant acceleration. At the end of the day, the whole story of motion is written in the steepness of the line.
And that brings us right back to where we started. It's actually true. With just a few simple rules, a single line on a piece of paper can clearly tell the entire story of a journey, turning some pretty complex physics into a simple, visual story anyone can understand. So I'll leave you with this final thought. We've been looking at these perfect, clean, straight lines. But what about the real world? Think about your own morning commute. All the stops and starts, the traffic, the sudden bursts of speed. What kind of wonderfully messy, jagged line would that story tell? Now, you've got the tools to actually picture it. Have you ever been on a merry-go-round? Or maybe one of those super fast spinning rides at an amusement park? You know the feeling, right? You're going at a totally steady speed, but you feel this force that's trying to throw you off the ride. Well, that feeling, that mysterious push, is actually at the heart of some really cool fundamental physics. And today, we're going to figure out exactly what it is.
Okay, so let's start our investigation. To really get this, we first have to set up the mystery. We need to look closely at what's really going on when something moves in a perfect circle. So here's the core puzzle, the big question. You're on that merry-go-round, chugging along at a nice, constant speed. The speedometer, if you had one, wouldn't be changing at all. So why do you feel like you're being pushed? Why do you have to hang on so tight? I mean, constant speed should mean no forces, right? That's what makes sense.
And yeah, I know, it totally seems like a contradiction. It feels like it breaks the rules, but I promise you, by the end of this, it's going to make perfect sense. The answer is just hiding in plain sight, right in the details of what it means to move in a circle.
So, to solve this little puzzle, let's start by being detectives. We're going to break down the name itself. Uniform circular motion. Seriously, all the clues we need are hidden right there in those free words.
Let's just look at this. Motion. Okay, easy enough. Something is moving. Circular. Also pretty straightforward, right? It's moving in a circle. But then there's uniform. This is the part that tricks everyone. It just means your speed, say 10 miles per hour, is locked in. It doesn't change. Now, each of these ideas is super simple on its own. But when you put them all together, well, that's where the physics gets really interesting.
And this brings us to the big plot twist in our story. Because even though one thing, your speed, is staying perfectly constant, something else, something incredibly important, is always changing.
Okay, pay attention, because this slide right here is the absolute key to the whole thing. See, in everyday life, we kind of throw the words speed and velocity around like they're the same thing. But in physics, no way. They are totally different. Speed is just the number on the dial, 10 miles per hour. That's it. But velocity is that speed plus the direction you're going in. So while your speed on that merry-go-round is constant, your direction is changing every single second. Just picture it like this. Imagine there's a big arrow attached to you pointing in the direction you're moving. That's your velocity arrow. As you go around and around that circle, that arrow is constantly turning. Pointing this way, now this way, now this way. It never stays pointed in the same direction for more than a split second.
And that leads to this mind-blowing reveal. In physics, acceleration isn't just speeding up or slowing down. It's any change in velocity. And since your velocity's direction is always changing when you move in a circle, that means you are constantly accelerating. Yep, even with a perfectly constant speed, you're accelerating. Let that sink in for a second.
Okay, so if you're accelerating, that immediately leads to the next question. What's causing it, right? I mean, accelerations don't just happen out of nowhere. Something has to be behind it. And good old Isaac Newton gave us the answer right here. His first law basically says that things like to keep going in a straight line at a steady speed. To change that, to change the speed or the direction, you have to push it or pull it. You need a force. Your body wants to fly off in a straight line, but something is forcing it to turn. And here it is. The name of that force, the culprit behind this whole mystery, is centripetal force. And the name is perfect because it literally means center seeking. It's this constant inward pull toward the center of the circle that's responsible for changing your direction and causing that acceleration. Think about swinging a ball on a string over your head. The tension in that string is the centripetal force. It's like an unseen hand that's always pulling the ball inward, stopping it from flying away. And if you suddenly cut that string, what would happen? The ball wouldn't fly straight out from the center. Nope. It would shoot off in a perfectly straight line, tangent to the circle, in whatever direction it was going at that exact moment.
All right, now for the really cool part. Let's zoom out and see how this one simple idea isn't just for amusement park rides. It is absolutely everywhere, running the show from the giant cosmos all the way down to your laundry room.
Get this. The sun's gravity, that's the centripetal force, keeping Earth in orbit. The friction between your car's tires and the road when you take a turn, that's the centripetal force pulling your car into the curve. The wall of your washing machine during the spin cycle, it's providing the centripetal force that pushes the water out of your clothes. It is the exact same physics over and over again.
And that brings us right back home to our merry-go-round. That push you feel pushing you out, it's not a real push at all. It's just your body's inertia. It's your body trying its very best to go in a straight line, while the ride is constantly forcing you inward to turn. What you feel is your own resistance to that change. And just like that, the mystery is solved.
But that leaves us with one last, really fascinating question to think about. If all the real physics, all the real forces are pulling you in towards the center, then why does every single instinct in your body scream that you're being thrown out? Well, that feeling, that's a whole other story. It involves something we call a fictitious force, and it's a topic for another day.